You ready? I can hear Drake saying, oh, this one has directions. This is a very vector-intensive unit. Mr. Dewick, how does the difficulty of this unit compare to some of the other ones? I would probably call this the second toughest one of the year. The math is going to be pretty intensive. I strongly encourage you during this unit, have your calculators out and do the math, do the calculator work with me. The actual equations, there's only two. And we're going to start out today, as always, reviewing Physics 11. But then after the break, we're going to jump with both feet into the deep end of Physics 12. Okay? This is one of those units you don't want to fall behind and think, oh, I can just catch up on everything. That would be a bad call. Momentum. One of the most important concepts in physics is the idea of momentum. It ranks right up there with energy. Newton first used the concept when he phrased his second law of motion. We said that Newton's second law was F equals ma. He never actually said it that way. He actually phrased it in terms of momentum, and I'll show you how he phrased it a bit later. He called the product of mass and velocity the quantity of motion, but over time, instead of calling it quantity of motion, we call it momentum. It's the amount of motion an object has. And what makes momentum so important is the fact that, like energy, it's also a conserved quantity. The amount in an isolated system with no outside sources of momentum or energy, the total momentum of the objects before a situation and the total momentum of the objects after a situation will remain constant. But Drake, because momentum is a vector, we're going to have to be way more careful with our before and after equations. You're going to be adding things tip to tail like crazy. So, any moving object has momentum. We would love to use the letter M for momentum. Wait a minute, M is already taken. What do we use the letter M for? Mass. So because it's a product, we use P. And it's calculated by multiplying the mass times the velocity. Or we say this, P equals M times V. Now, mass is a scalar, which means the direction that momentum has, because it is a vector, will be the same as the direction that the velocity has. What would the units be? Well, what do I measure mass in? What do I measure velocity in? The units for momentum are kilogram meters per second, and they haven't shortened that one. The same way that a joule was a Newton meter, but we called that a joule. The same way that a Newton was a kilogram meter per second squared, but we called that a Newton. This one hasn't been shortened yet. I think I mentioned to you folks last year, there is a movement afoot right now to rename a kilogram meter per second an Einstein, because he doesn't have a unit named after him. That might happen in the next 15 or 20 years. It's a slow process, but I'd be for it. Momentum, oh, this is key, is a vector quantity, which means when you're adding momenta, which is the plural of momentum, when you're adding momentums, we have to use vector addition. If everything is in a nice straight line, we have to let one direction be positive and one direction be negative. If things are at angles, we're going to add stuff tip to tail, and typically the angles are going to be yucky in such a way that trying to break everything into components is going to become onerous. It's doable, but it's more work than just diving in, sucking it up, and learning how to do the trig. So I'm going to say we're going to dive in, suck it up, and learn how to do the trig. I said Newton's second law, F equals ma, can be written in terms of momentum. So F equals ma, well, really, that's mass times change in velocity over change in time, because the definition of acceleration was a change in velocity over a change in time. That's where the v final minus v initial over t came from. We said, Rebecca, time was always a change in, so we got sloppy and stopped writing the delta. This is really going to be mass final minus initial over time? Which is really mv final minus mv initial over time. If I take the time to get rid of brackets. But from the box up above, what did I say mass times velocity was? From the box up above, what is the product of mass times velocity called? Momentum. So this ends up being final momentum minus initial momentum over time. They're vectors, they're vectors, they're vectors. By the way, what is final minus initial the same as? This is how Isaac Newton gave his F equals ma. He wrote it as the change in momentum over time, but that really is ma, if you work backwards through the argument, Simone, that I just gave you. Okay. So, in English, Newton's second law, F equals ma, can be stated in terms of momentum as follows. An unbalanced force, a net force, acting on a body changes its momentum, changes its motion. And the rate of change of momentum, because when you divide by time, that's always a rate of change, is equal to the unbalanced force. Force is mass times acceleration, yes. Force is equal to how fast you're changing the momentum of an object. The rate of change of momentum. It's a different way to think about force. Another key term is impulse. I'm going to be using this word an awful lot. Okay? If I take the equation that we just derived and I times the t over to this side to get the change in momentum by itself, we get force times change in time equals change in momentum. Instead of writing delta p, I wrote delta mv, because that's momentum is mass times velocity. We call that impulse. Impulse is defined as change in momentum. Nick, what's impulse defined as? When I say impulse, what do I really mean? Say the same thing. When I say impulse, what do I really mean? Say the same thing. What's change in momentum the same as? And what's change in anything always? See, this is the sequence that bugs the heck out of me because kids forget. I guarantee, Nick, on your test, I'm going to ask you to find the impulse. And people will freak. No. What's another word for impulse, Ty? And what's change in anything, folks? Really, all I'm saying is please go find the final momentum of the object, find the initial momentum of the object. If they're in a straight line, go final minus initial. If they're at angles, subtract them vectorially. How do we subtract vectors? We don't. We add the opposite. Okay. If you're a Star Trek fan, you may recall Star Trek always talked about impulse engines. What they really meant was engines that were changing the momentum of the Starship Enterprise. How would you change the momentum? Well, you're not changing its mass. I guess you're changing its velocity. Impulse engines. Okay? So they picked that word for a reason. Someone there had a good physics background. Well, a lot of people on that show had good physics background. How can you change the momentum of an object? Well, you can have a large force acting for a short time. Think a locomotive hitting a parked car. That'll change the momentum of that parked car. The large force is the locomotive. You can have a small force acting for a long time. This might be, we're hoping, in fact, they're testing it, I think, right now, a new space drive that fires a tiny amount of mass out the back. The acceleration is really tiny, but if you do it for 3 or 4 months, eventually you get going pretty fast. The biggest impulses would be large force for a long time. That'll really change an object's momentum. Well, like what a locomotive does not when it hits a train, but when it tugs a boxcar, it over time changes its momentum quite substantially. You had a hand up. Yeah, hustle back. Nerd moment. The new drive, the new space drive that they're talking about, if you've read nerd blogs like me, you've come across it. NASA is just testing it out. It may violate Newton's third law. It's what we're calling a reactionless drive. Newton's law is often called the law of action-reaction. For every action, there was an equal and opposite reaction. There seems to be this space engine that generates a very tiny, tiny, tiny force, but there is a net force, and there ain't no mass coming out the back, which means there's no action to cause the reaction. The paper was first published about 5 or 6 years ago. I'm keeping track of this because if this was the case, if Newton's third law was a special subcase of some higher level of physics that we haven't discovered yet, that would be nice for space travel. It might cut the trip to Mars down to a few months as opposed to 8 or 9 months or a year. And in particular, it would mean you'd have to carry way less mass. Right now, all rockets have to carry their mass to eject out the back to go forwards, which is why the Saturn V rocket, if you ever see it live, I think it's like 30 stories tall to get this tiny, tiny thing up there. The rest is filled with massive fuel. So a little nerd trivia for you. Not on your test. We'll see. The consensus is maybe, because the force is so small, maybe we're making a measurement error or there's something else going on, but NASA is testing it. Hey, what are the units for measuring momentum and impulse? What were the units for momentum? Mass times velocity, kilogram meters per second. And if impulse, what's another word for impulse, Nick? You know what? Impulse is also measured in kilogram meters per second. Wait. I also said that another way to calculate impulse was force times time. Nick, what do I measure force in? What do I measure time in? So, impulse can be measured in Newton seconds or kilogram meters per second because change in momentum. What's another word for change in momentum? Which is final minus initial is also force times time. The equation that you have on your formula sheet, by the way, we've done all of the equations for this unit already. On your formula sheet, you have two equations. This one, momentum is mass times velocity, and then you have the impulse equation. That momentum is change in velocity. Sorry, impulse is change in velocity. Velocity, God, I said it again. Impulse is change in momentum, which is force times change in time. So, which units do you use for impulse? Max, I don't care. I'll give you full credit for both. Typically, if I have found the impulse when they gave me a force and a time, I'll probably write my units as Newton seconds because that's in my brain right then. If I have found the impulse by going the final velocity minus the initial velocity, mass times mass, then I'll probably write it as kilogram meters per second. But they are equivalent units. Newton seconds is equivalent to kilogram meters per second. Momentum can be expressed in either units, so can impulse. I won't be fussy as to which is which. And this brings us to the law of conservation of momentum. There should be thunder and lightning, but we won't worry about it right now. The total momentum of an isolated system will remain constant. We're typically going to write it this way. What is that a symbol for? Although typically in math you write it like this, but I typically get lazy and don't write it that nice. What's that an abbreviation for? It's a sigma. What? The sum or the total. The total momentum before something happens equals the total momentum after something happens. In fact, probably much like a free body diagram, Probably, much like if there's a change in height, change in speed, curvy path, I go conservation of energy. Probably, like if it says work or it asks work and there's no distance, I go change in kinetic plus change in potential. If there is a collision, I start out with the sum of all the momentum beforehand equals the sum of all the momentum after. This is going to be one of my go-chooses. Okay? You might have noticed that I've been paying way more attention to my vector notation. Yeah, Drake, you were correct when you were muttering earlier, stuff has lots of direction. Yeah. In fact, in momentum problems, there are almost always going to be changes in direction, because when you have a car crash or a collision, I don't think things keep going in a straight line at a steady speed the same way they were before. So to remind myself, I won't take marks off if you don't put vector notation, Sarah, but to remind myself, be careful with directions, I will be very fussy for myself with my vector notation. We just finished a unit with scalar math. This one, vector math. Example 1. If conditions are such that this car and this truck end up at rest, you know what? I would probably underline the phrase at rest after this collision. How can we say that momentum has not been lost for the system? First of all, how do we calculate momentum? Let's write it right here since you've turned the page. Momentum is what times what? It's mass times velocity. You'll probably memorize that equation during this unit because you get sick of looking it up. What's the final velocity of the truck? 0. What's the final velocity of the car? 0. So what's the final momentum of this system? 0. You know what the initial momentum of this system was? 0. Now that bugs kids because they're saying, how can you say the momentum was 0 when stuff is moving? Well, let's find out. Before the collision, we have the momentum of the truck and the momentum of the car. And I've just told you, ready, Robbie? First one, here it comes. Wham, they collide. And they come to a final momentum of 0. How can this be true? Momentum is what times what? Mass times velocity. Okay. Duncan, what's the mass of the truck? 2,400. What's the velocity of the truck? Plus, what's the mass of the car? What's the velocity, not the speed, what's the velocity of the car? Negative 24, because it's in the opposite direction. I think the first term, Robbie, works out to 24,000. I think the second term works out to negative 24,000. Robbie, in your head, what's positive 24,000 plus negative 24,000?
0.
In other words, the amount of momentum you had before you started was, same answer,
0.
and the amount of momentum you had afterwards was,
0.
momentum was conserved. Momentum was conserved. Okay? It's because momentum is a vector. You're not violating the laws of physics. A whole bunch of energy vanished. Well, you know what? All of the kinetic energy went into deforming the vehicle's force times distance. Oh, and probably a lot of heat was generated during the collision. Lots of sound was generated during the collision. So energy was conserved as well. It's just that that went into deforming things. The law of conservation of momentum can be written in several ways. I tend to start here because it's the shortest. Again, this says the total momentum beforehand, initial, equals the total momentum after, final. The reason I start there is it's the shortest. Then, I'll break it up into something kind of looking like this, but it depends. I'll ask, is stuff moving? Is it not moving? Well, you know what? Let's do one. By the way, we use the law of conservation of momentum when there is a collision or an explosion. I think I made the joke last year. We use it when there's a collision, explosion. This is a job for conservation momentum. Unless the question starts talking about impulse, then I might try solving it using force times time equals change in momentum. A rifle bullet of mass 0.06 kilograms leaves the muzzle of a rifle with a velocity of 600 meters per second. If the 3-kilogram rifle is held very loosely, with what velocity will it recoil when the bullet is fired? Is this an explosion? This is a job for conservation of momentum. I would start out by saying the total momentum before we pull the trigger equals the total momentum after we pull the trigger. It looks like this question has two objects, the bullet and the rifle. Before we pull the trigger, what's moving? The bullet, the rifle, both, or neither? I think neither. You okay with that? So what's my initial momentum if nothing is moving? Come on, eraser. Come on. Eraser is on there. Boy, take a little bit of a delay here. 0. Bang! We pull the trigger. That was low. Yeah. After we pull the trigger, what's moving? The rifle, the bullet, both, or neither? Both? Stuck together or separate? So I'm going to write this. Momentum of the bullet final and momentum of the rifle final. And this year, now, once we have our starting equation, we're going to have to pause. And we're going to say to ourselves, self, are there any angles mentioned in this question at all? If there were angles, we would now move to vector math. I think in this question, though, everything, James, is in a nice straight line. You okay with that? Momentum is what times what? Right? We wrote that at the top of the page, I think. Yes? So I'm going to get this. 0 equals the mass of the bullet, velocity of the bullet after we pull the trigger, final, plus mass of the rifle, velocity of the rifle, final. What's this question wanting me to find? Wants me to get that by itself. Again, are there angles in this question? No, then I can do this algebraically. If there were angles in this question, I'd have to be drawing things, adding them tip to tail, and doing trig to get this. We're going to see something like this next lesson. For now, I think what I could do is I could minus the mass of the bullet, velocity of the bullet, and I think I would divide by the mass of the rifle. I think that'll give me the velocity of the rifle. Is that right? Yes, I think. Let's see what we get. The velocity of the rifle is going to be negative mass of the bullet 0.06. 600, 6 times 10 to the 2, divided by 3. I think I can do this in my head because 600 divided by 3 is 200. 200, negative 12? Or negative 1.2. No, negative 12, I think. Yeah? My pen is really acting slow when I'm changing colors. There seems to be a big delay. It's driving me crazy. Negative 12 meters per second. Now, what's the negative telling me here, Drake? Because you talked about direction. I'm glad you remembered that. If the bullet went west, the rifle recoiled which way? East. If the bullet went north, the rifle recoiled. If you know what, let's keep it just generic. If the bullet went forward, the rifle recoiled backward. Okay? I wouldn't make you say that. I'm fine with the negative, but I'm telling you, whichever way the bullet went, the rifle went in the opposite direction. Put your pencils down, look up. Football. Where's my football players? Former or current? Okay. Beautiful physics, because beautiful collisions in football. Last year, I had to have all our collisions be head-on. Most tackles are not head-on. They're from an angle on the side. We'll talk about that how that works this year. Even better, because in football, the grass, there's friction, and actually it isn't a perfectly conserved system because lots of the energy goes into your treads of the grass. Hockey body checks on ice are really nice examples of conservation and momentum. Some of the best examples are curling. The only problem with curling is all the masses are identical, which means the m's always cancel, which means you might make some assumptions about the laws of physics that aren't quite true. Because if masses are identical, that gives you some other rules. Hockey, the masses are not identical. But in football, Ty, what's A want me to find? What's A want me to find? Okay, momentum is mass times velocity. Ty, what's the mass of the football player? What's his velocity? How much momentum does this football player possess? Whatever 112 times 4.8 is, which is, Mr. Dewick? 112 times 4.8, 537.6. Is that right? I'll call it 538, but I'll keep this number on my calculator. 538, Ty, what units? Well, what do I measure mass in? What are the units? What do I measure mass in? What do I measure velocity in? Yeah, so kilogram meters per second. Drake, what does B want me to find? To do what? Last two words. In other words, I want his final momentum to be 0. Okay? So, impulse is change in momentum. What do I want his final momentum to be? Minus, because change in anything is final minus initial. What was his initial momentum? Psst, the answer for part A. In your head, without a calculator, what's 0 minus 537.6? All right, negative 538 kilogram meters per second. Or you could write Newton seconds, but since I didn't use force times time, I'll use kilogram meters per second. What's the negative telling me here, Drake? If the original football player was running north, which way does the tackler have to hit him? What's the negative here telling me? If the original football player is running north, which way does the tackler have to import an impulse? South. In other words, you got to hit the guy in the opposite direction he's moving, which, again, you guys have figured out as athletes, but there's the physics behind it. James, you going to make it? Because I'm coming at you next. James, what's part C want me to find? Average force. James, what did I find in part B? It would be cool if there was an equation for impulse for change in momentum that had a force and a time in it. There is. This is the only other equation for this unit from your formula sheet. It says force times time equals impulse, change in momentum. James, what does this question want me to find? How would I get the force by itself? Divide by time, which, since time is a scalar, that I can do no problem. I'm not dividing by a vector here. So I'm going to get this. The average force is going to be change momentum over time. Okay. So I'm going to get negative 537.6, is that what it was? Yep. Divided by 1.2. What do you get? $537.6 negative divided by 1.2. You get negative 448? What's the negative here telling you for the force direction? Again, coming back to Drake, if the player is running north, the force has to be applied which direction? South. you know what? Let's keep it generic. If the player is moving forward, the force has to be applied. Now, how long did this tackle last, Drake? How many seconds? That's a long tackle. Okay, this would be when someone wraps their arms and gets dragged for a while and takes a while to bring them to a stop. Okay? Drake, if this time value got smaller, what happens to the force? Gets bigger. This is the massive quick hits, because the time value is so short when they blow up somebody coming across the field or whatever. There has to be a massive force. Otherwise, there's no way you could cancel out his momentum. It goes back to the very, very beginning when I said an impulse can be applied by a large force acting for a short time. Those are the massive hits or the massive body checks. Or a small force acting for a long time. In hockey, I can blow someone up in a massive body check, or for 5 seconds I can slowly ride him into the boards and change his impulse that way too. I'll get the same result. I'll change his impulse, I'll change his momentum. The fans like the earlier ones, but also now we're cluing in it's not that healthy and we're cracking down on concussions and things like that, right? Is that okay? Drake? Yeah, a little football physics for you? Okay. So imagine you're an astronaut. You're doing a spacewalk outside the space shuttle, but you're using that little motorized jetpack rocket pack that they wear, not a cable. And your small maneuvering rocket pack suddenly quits on you and you're stranded in space with a velocity of 0. But you do have a $50,000 camera in your hands. How can you get back to the space shuttle? Throw your camera away from the space shuttle. By the way, is it possible before you even do that, floating in space, could you turn yourself so that your back was towards the space shuttle so that you could throw it forward? We saw a video how in 0G you can actually turn yourself, and then you throw the camera away from the space shuttle. Why does that work? What's your momentum right now? 0. What must your momentum be after you throw the camera? Still 0. So if the space shuttle is to the east, doesn't make sense in outer space, but we'll go with that. If you throw the camera to the west, you must pick up a small velocity to the east. Same momentum, but since your mass is so much smaller, you're going to go way slower. Okay? So, throw camera away from shuttle. It'd be expensive, but it would save your life. Okay. Impulse and momentum really, really come to play when we talk about how rockets work. I went on a bit of a rant about how NASA is testing out this inertia-less drive, this reaction-less drive, this drive that might violate Newton's third law. We're going to pretend that that doesn't exist because we're still not convinced that it does. It's still very much being tested. All of our current rocket technology, the reason it's so tough to go to Mars, for example, you have to bring all of the fuel, all of the mass to eject out the back of your rocket with you. This is why even if going to Mars, probably the first Mars mission is not going to land, because to land, you have to have all that mass to eject out the bottom of the rocket to land and to take off again. If you haven't read the book, The Martian, he offers some very clever solutions to get around that with technology that's reasonably doable right now, well worth the read. A rocket expels 1.2 times 10 to the third kilograms of gas each second. The gas leaves the rocket with a speed of that. Will the thrust produced by the rocket be sufficient to lift it if the force of gravity on it is that? Any suggestions on how I might want to start out here? So how much impulse are we getting out the back of our engine? Well, I'm seeing a mass times the velocity, but what units are those in, Connor? The very last one here. Do I have an equation that has Newton's force in it too? Let's see if we can figure out how many newtons of force we'll get from this engine. Oh, and if it's bigger than the force of gravity, we're good to go. Okay? I'm going to solve for F, and I'm going to hope that F is bigger than that. If it's not, this rocket's not getting off the ground. You okay with how I put that together? In other words, right now, this is not a collision. I haven't gone the sum of all momentum beforehand equals the sum of all the momentum afterwards, or wham, they collide, or anything like that. I guess here, the force from the engine is going to be that. Which is going to be the final momentum of the rocket gas minus the initial momentum of the rocket gas over time. By the way, what do you think the initial momentum of the rocket gas is? 0. It's going to start at rest because it's in a tank. Okay? So we can say this. What's the final momentum going to be? Well, mass v final and then time. Connor, what's the mass that we're ejecting? I'm going to write 1200 because that's less writing. What's the velocity that's leaving at? $50,000? Oh, I don't see a time. Or do I? Oh, each second. I was sneaky. The time is 1 each second. 1 second. Okay. I think we're going to get 6 times 10 to the 7th. Double check me. Yeah, 6 times 10 to the 7th? Yes? How many newtons is gravity on this rocket? What's the weight of this rocket? 5.8 times 10 to the 7th. What's the thrust of our rocket? 6 times 10 to the 7th. Will this rocket get off the ground? Yeah. You could even, if you wanted to now, do a lovely little free body diagram. You could even find the acceleration. You would say 5.8 times 10 to the 7th. 6 times 10 to the 7th. Yes. The rocket will lift off. But if I knew the mass of the rocket, I don't. I know the mass of the gas. I don't know the mass of the rocket. If I knew the mass of the rocket, Mikhail, I could find A. And then I could do all sorts of nice stuff. Okay? A 3.2 cart traveling 2.2 meters per second collides with a stationary, you know what? I think the word stationary tells me something. 1.8 kilogram cart. And they stick together. What is their common velocity after the collision? After the what? This is a collision? That's a job for conservation of momentum. Not force times time equals impulse. This is a job for conservation of momentum. The sum of all the momentum beforehand equals the sum of all the momentum afterwards. I've written something down. I feel better. I know I'm going to solve this. Sarah, let's call the 3.2 kilogram cart mass 1. Oh, how about instead of mass 1, mass A? And let's call the 1.8 kilogram cart mass B. Typically, the first mass that I see, Sarah, I'll call mass 1 or mass A. The second one, I'll call it mass 2 or mass B. Before the collision, what's moving? Mass A, mass B, both or neither? Mass A. So we have momentum of mass A initial. Wham! They collide. I got Rebecca too. After the collision, what's moving? Mass A, mass B, both or neither? Read the question. Tori? Stuck together or separate? So I'm going to go momentum of both final. Momentum of both final. Now, in Physics 11, we would keep going, Nick. From now on in Physics 12, right here, once we've written our momentum equation, we pause. Are there angles in this question? Say no. There will be. If there was, I could not go any further algebraically. I'd have to go further by drawing pictures, by drawing arrows, by adding tip to tail, and by doing trig. No angles here, though? Cool. I can do this algebraically. It's going to be mass A, velocity A initial equals, I guess, mass A plus mass B. They stuck together. V final. What am I trying to find here? Sam, what am I trying to find here? That one. How would I get that one by itself, Sam, my friend?
You would divide the joint masses.
Okay, so I think the final velocity is going to be mass A, velocity A initial, divided by mass A plus mass B. It's going to be mass A, 3.2, velocity A, 2.2, divided by 3.2 plus 1.8. I get 1.41. You have the notes? I give them to you. Yeah. 1.41 meters per second. Is anybody else? Yes? No? Yep. 1.41 meters per second. I guess forwards. So I guess we're imagining we had one mass sitting still, another mass coming towards it. They collide. They stick together. They move forward. Got a couple of video experiments for you.